So I'm really excited to be here today to talk to you about a new project some of us are working on at MIT. And this project is called BRAD, and it's about simplifying cloud data processing with learned automated data meshes. So this is joint work with Tim, Tianyu, Sam, Marcos, Amadou, Zinu, and myself, Jeffrey. So let's get started. So meet Tim the Beaver. For those of you who don't know, Tim the Beaver is MIT's mascot, and that's because beavers are resourceful and capable engineers. And naturally, one day, a startup comes to him for some help in building out their cloud data infrastructure. And so he turns to our community for some advice. So what does a typical cloud data architecture look like nowadays? Well, an organization might typically start out with a single database system, usually transactional, so in this case, AWS Aurora. They run everything they need here, so transactions and simple analytics. But of course, as business needs change, as they grow, they might decide that they need to run more analytical queries, and these might start interfering with the workloads that you run on Aurora. And so they might spin out a data warehouse, such as Snowflake, to run those analytical queries. Okay, all is good, but then as things progress, they decide that they start wanting to archive some of their data onto an object store, like S3. And naturally, once you have data on S3, you want to query it as well. So let's say this organization chooses to use BigQuery Omni because it has some features that they're interested in. One day, some people in the organization start realizing, hey, some of my dashboards are running a lot slower than I expected. And they discover this is because there are data scientists running big exploratory queries on the data warehouse that ends up slowing down the dashboarding queries. And so the organization decides to spin out another data warehouse to run these exploratory queries. Okay, all is good. But then as their needs continue to expand, they decide that they want to start running more involved pre-computations on all of their analytical data. So they start spinning out an EMR cluster to run these jobs and to extract, transform, and load more of this data back and forth between the object store and their data warehouses. So right away, we can see that we started out with a very simple single system architecture and quickly ballooned to this multi-system architecture where you have many specialized systems, each for different parts of the workload. And this is what's typically called a data mesh. But in fact, this is actually a simplified version of what you might see in reality. So these are some architecture diagrams we found that show far more systems working together in a much more complicated mesh. So at this point, it's more of a data mess. So Tim the Beaver realizes that his job kind of sucks. He needs to go and pick a transactional engine. He needs to figure out which data warehouse to use. He might want to set up a data lake execution engine. And of course, with all of these systems, he has to set up data pipelines to move data between the systems. And moreover, beyond just choosing the software systems to run, he also needs to decide what kind of instance types or which hardware to use to run all of these systems. Now, Tim the Beaver is a smart guy, so with some time, he can probably figure all of this out, right? But his job doesn't end there. He also needs to help others in his organization figure out which systems in the mesh to use for their workloads. So where should they put their data and where should they send their queries? So it turns out that picking the right system can actually matter quite a bit. So we ran an experiment where we ran queries on Aurora and Redshift, and we configured these two systems with similar amounts of hardware. So for those who are not as familiar, Aurora is a transactional database, and Redshift is a data warehouse, so it's an analytical database. So we ran two queries that have the same join template that were adapted from the join order benchmark. So on the plot on the right, the y-axis is query runtime, so lower is better. And you can see on this first query, query A1, it kind of behaves intuitively as you would expect, in that Redshift is 3.7 times faster than Aurora. And this makes sense given that this is an analytical query and Redshift is an analytical database. But what's interesting is that query A2 ends up being 17 times faster on Aurora than Redshift. And the reason for this is that query A2 has some predicates that are highly selective. And it turns out that these predicates are on columns that are indexed on Aurora. So Aurora can use these indexes to run the queries much faster. So the takeaway is that running all of the analytical queries on Redshift might not always be the best choice. And the reason we ended up here is this mantra of one size does not fit all. And this has led to specialization. On the slide here, I'm showing the different services that are offered by AWS on the left and Google Cloud under the database and analytics categories. So specialization is not necessarily a bad thing because you get state-of-the-art performance for your specific workload. But on the flip side, specialization leads to a paradox of choice. Now users need to figure out which systems they should be using for their workloads. So a group of us at MIT got together and started thinking, can we help make Tim the Beaver's job easier? Right? There's too many choices for Tim the Beaver and others who are in his shoes. This is not a problem that's unique to Tim the Beaver. This is a problem that's shared by many small and mid-sized companies. And users don't often care about the specific choices. They just want something that works well enough, and they also want less complexity. And moreover, they want to get the most value out of the money they spend in their infrastructure. So the holy grail really is having one system that can have state-of-the-art performance for every possible workload. But more importantly, we want to do this without discarding all of the work that has gone in to build all of these specialized systems. Getting a data system ready for production takes a lot of effort, and we don't want to throw all of that away while just building yet another system. And so that's where Brad comes in. So the idea behind Brad is to have one interface fitting most. So Brad abstracts away a mesh of specialized cloud database engines as one system. And Brad will pick the best engine or multiple engines for that workload. So this could be sending a query entirely to one engine or splitting it up and running it across multiple engines and stitching the results together. And the reason why you might want to do that is if certain parts of the query run faster on certain engines. Of course, Brad autonomously manages the data mesh. So this means adding, scaling, changing, or removing engines to the mesh as needed. And Brad also optimizes the mesh for performance under a cost budget or vice versa. I also wanted to emphasize here that Brad's data mesh optimizations go beyond just picking an instance size for a provisioned engine. Brad is able to move entire query workloads off of one engine onto another. So it's about picking the engines to put into the mesh, choosing where the queries go, and also considering this in relation to performance and cost, which I'll highlight later in the talk. And finally, users interact with Brad using SQL just as they would any other database system. They see one system, even though under the hood, Brad is implemented using a mesh of specialized engines. So now some of you looking at this figure might be thinking, hey, this looks a lot like a Polystore. What about prior work on Polystores? And our answer is that Brad is a Polystore, but it's a next generation Polystore, and that the system landscape has changed enough that it warrants new solutions. And this is for three key reasons. The first is that Brad tackles the cost-performance trade-off in the modern cloud. Historically, we were really concerned about making the most out of the hardware that we have available. But theoretically now in the cloud, we can use as much hardware as we need. We just need to be willing to pay for it. So now there's this interesting trade-off between cost and performance that Brad needs to tackle. The second is that Brad uses one data model, which is the relational data model, and this simplifies cross-engine optimization, such as running a query across multiple engines. This is in contrast to prior work on Polystores, which was really about bridging multiple data models together. And finally, we envision that Brad will leverage all of the recent work on applying machine learning to optimize data systems to help manage and automate the management of the data mesh. So the road to Brad is filled with many research challenges, and I'm just showing a few of them on the screen now, and we discuss many of them in more detail in our vision paper. But I did want to focus on and highlight one of the research challenges, which is really the essence of Brad, and that is joint data mesh, query, and cost optimization. To really understand this challenge, let's zoom out a bit and go through an interesting example of a situation that Brad might face. So suppose we have 3 queries running on Brad, and Brad is concerned with determining where to send the queries. So concretely here, we're just considering 2 engines, Redshift and Athena, and Brad wants to run an entire query on one of these 2 engines. So conceptually, the natural choice is to choose the engine with the best predicted performance. And on this plot, I'm showing the actual query runtime. So the y-axis is the query runtime and lower is better. And you can clearly see that Redshift is definitely the better choice here as it has a faster runtime on all 3 queries. And so that's the natural choice. But what if I told you that these were reporting queries? So they run regularly, but they run once every hour, pretty infrequently. And at the end of the day, the users really only care that they complete within 30 seconds. So in this scenario, the decision landscape changes once you start considering other aspects of the data mesh. For example, cost. So on this plot here, the x-axis is the monthly operating cost, so lower to the left is better. And it turns out that this workload ends up being 7.5 times cheaper to run on Athena than Redshift. And the reason is that Athena is serverless, so you're charged based on the amount of usage that you have, in particular the amount of data you scan. Since these queries run infrequently, once an hour, it ends up being better to run them on Athena in terms of cost than to pay to provision an instance of Redshift. So the takeaway here is that the best performing engine might not necessarily be the most desirable once you consider all of the aspects of the data mesh. And potentially the right decision for Brad to make here is to move the workload off of Redshift, shut it off, move the data onto S3 so that it can be accessed by Athena, and then route all of those queries onto Athena. So this example shows that Brad really needs to consider all aspects of the data mesh when making even a conceptually simple decision, such as choosing which engine to use to run a query. And these aspects include which engines you put into the mesh, how you provision them. This also influences where you place the data. And of course, all of these factors depend on the workload and also influence the operating cost of the entire mesh. So we call this problem the joint mesh query and cost optimization problem in Brad. We discussed this in more detail in our vision paper, so I'd encourage you to check that out if you're interested. But at a high level, we approach this with 3 steps: proposing a set of candidate mesh changes, predicting how each of these changed meshes might perform on the workload and their cost, and then of course selecting the best candidate mesh. To give you a little bit of intuition, for proposing the set of candidate mesh changes, we can use heuristics such as routing all transactions onto Aurora and deciding to place tables on the engines where you want to run the queries. But we can also potentially learn such an exploration policy using an offline exploration phase in a reinforcement learning setting. To predict the performance of a workload on a mesh, we use learned query runtime models, which are typically called cost models. A key differentiating factor here is that Brad's models cannot rely on physical query plan features. And the reason for this is that Brad might be considering whether or not to start up an engine to run a workload onto it. So the data is not present on the engine, and the engine is not even running. So then you cannot get a physical plan from that engine. So the models that Brad use cannot always depend on those features being available. So I wanted to leave you with an example of Brad in action. So here a user is running queries and they want them to complete in under 10 seconds, which is the line shown on the plot on the top. And then the plot on the bottom is the monthly operating cost of this data mesh. So they're using a data mesh with just Redshift running with a single RA3 XL Plus node, which is the default node type that's recommended when you start a new cluster. And the x-axis here is the elapsed time. So when they run the queries, they find that all the queries run under 10 seconds, which is fine. But when Brad's optimizer runs, which is the dotted line here, Brad correctly predicts that you can run the same queries on a DC2 large instance and still remain under this 10-second budget. So the dashed lines here are Brad's predicted runtimes, and the solid line is the actual runtime. So Brad makes this change to the data mesh and helps the user save 4 times on operational costs. So there are a lot of other details that I didn't have a chance to talk about in this talk, so I'd encourage you to check out our vision paper for some more details. So this includes a discussion on items such as data consistency across all of the engines, how we build transferable query runtime models, how to handle table transformations and ETLs across the engines, how we might automatically handle translating between SQL dialects of all of the engines in the mesh, and also how we can ensure that Brad can be gradually adopted onto an existing data mesh instead of having to require users to start an entirely new data mesh to run Brad on. And so Brad simplifies data mesh creation and management with 3 key ideas. Brad uses one unified interface over a mesh of specialized cloud database services. It leverages learned models and policies to help automate the data mesh use and management. And it helps users get the most value out of the budget that they have for their cloud infrastructure while still getting state-of-the-art performance. And most importantly, this allows Tim the Beaver to finally get back to his mascot duties. So Brad is a project that involves many people at MIT. We're really excited to hear from you if you have any questions or any ideas, so please don't hesitate to reach out. And thanks for listening to our talk.